Hey guys, welcome to the next set of notes. Our topic today is something called implicit differentiation, and that is essentially designed to address this problem right here. Find the equation of a tangent line to the given graph at the given point. So here's a point. This graph is a circle, as y'all hopefully remember from last year. The equation for a circle is something like something like that right there. X squared plus y squared equals 25. And normally what we would do here is we would just kind of we would just take the point which we were given for 3, and that's our point to plug in for x and y, and then we'd find the slope by taking the derivative and then plugging in 4 for x. But we can't really do that because you can't write this thing as like y as a function of x. If you're trying to solve this thing for y, you get something like y equals the square root of x. Nope. Something like y equals the square root of 25 minus x squared, but it's really plus or minus that. So there's really 2 functions you have to look at. There's like the bottom and the top, and so that's like not a very useful thing. So how do we do that? And the answer is by using this thing called implicit differentiation, which takes into account the fact that while the derivative of x squared is easy, it's 2x, the derivative of y squared with respect to x, I may not know what the answer to that is. So we always end up with equations that we have to take the derivatives of, and the equations have y's in them. And the acknowledgement here is that y is a function of x. So like we think about that, this right here, this y squared, we think about that as y squared. It's really equal to some function f of x squared. And so to take the derivative of this, I have to use the chain rule. That's basically what this comes down to. So some examples of this are this. So the derivative with respect to x of x cubed, we know this already. This is just 3x squared. And the reason I can use the power rule without worrying about any chain rules is because this x here matches that x there. Derivative with respect to x of x cubed is 3x squared, period. But it's different here. And what's different is that this is y and this variable here is x. So I don't know if maybe y is equal to x, in which case it's just 3y squared and we're done. But y could be something else. If I take the derivative of this, I use the regular rule, 3y squared. But since I don't know if y is a function of x, I have to multiply it by its derivative. So we would say the derivative with respect to x of y cubed is 3y squared times y prime, or sometimes we write it like this, 3y squared dy dx. So there's like this thing here, this extra piece comes from the chain rule. And it comes from the chain rule because we don't know if y is a function of x or not. It might be. And I don't know if it is, so I have to add this piece in case it is. And so the way this would look for something, there's a couple other functions here. So here's the derivative with respect to x of x plus 3y. So the derivative with respect to x of x is 1. We know that one already. Derivative with respect to x of 3y is 3, because the derivative of 3x would be 3. But then I got to multiply by the derivative of this because I don't know if it's a function of x. I mean, it is a function of x. I don't know if it's a complicated function of x or not. We could also write that like this. And another example here would be this last one. This is now a product of 2 functions, so I got to use a product rule. So I do the derivative of the first, which is 1, times the second, plus the derivative of the second. And now this is where I run into my implicit differentiation. This x here does not match the y. So whenever I see that, I have to use implicit differentiation. That means I take this derivative as though this thing is an x. So it'd be 2y. Leave the y in there. I got to multiply by the derivative of this though. 2y times dy dx. And that's how implicit differentiation works. It works like whenever you're taking the derivative with respect to some variable of some other variable, you got to add this dy dx piece. chain rule. This is the chain rule coming into play. So the basic rule for this is take derivatives like you normally would, but if the derivative is with respect to x and the thing here is y, you got to throw a dy dx in there when you take the derivative. You notice I'm using the same rules as before. Like the derivative of 3x is 3, so I just have a 3. The derivative of x squared is 2x, so I have a 2 times, in this case, y. And then always multiply by the derivative. And you'll see that y prime is sometimes easier to write because it's less to write, but it's not really any different from dy dx. These have the same meaning in these problems. So here's some like simple rules. We're going to differentiate both sides of some equation with respect to x. A bunch of dy dx's, or at least one, is going to pop out anytime we take the derivative of something with a y in it. And we're going to collect all those terms on one side of the equation and move everything to the other side. You'll see what this means in a moment. Then we're going to factor out dy dx, or y prime, depending on how we wrote it, and then we're going to solve for it. And you'll kind of see what I mean. So here's an example. Given this big stupid equation, find dy dx. So our first step was take the derivative with respect to x to both sides. So I do that. So I got y cubed plus y squared minus 5y minus x squared on the left, and the derivative with respect to x of just -4 on the right. And now I take some derivatives. So I got y cubed here. That's supposed to be a 3. And so the derivative with respect to x of y cubed is this, 3y squared y prime. I'm going to use y primes because it's shorter, but it's the same thing as dy dx. But you see, I took the derivative as though this was like the something to the third power. The rule is 3 times something to the second power times the derivative of the something. It'd be the same thing here. This is y squared, but it could easily be x squared. I don't know what it is, but I know the rule for squared things is 2 times the thing to the first power. That's 2 times y to the first. But then I got to throw a y prime in there because I don't know what y is. So I'd do y prime. Then I do this one, the derivative of -5y. Well, I know the derivative of -5x would be -5. So I do -5. And then this thing would go away, but I got to multiply by its derivative. Chain rule. Each one of these y primes represents an instance of the chain rule. Then I do minus x squared. Again, it's the squared rule, which is 2 times the thing to the first power, times the derivative of the thing. But here the thing is x. The derivative of x is 1, so I'm good. And now the derivative of -4 is equal to 0. That's a constant. So I've done the first step, which is take the derivative with respect to x of both sides. And I've used the implicit differentiation 3 times. Once here, once here, once here. I didn't really have to use it here because this was just something with x's in it. And now I collect everything with y prime on one side and everything without it on the other side. In this example, every term has y prime in it except for the 2x. So I'm just going to move that one to the other side. So I rewrite 3y squared y prime plus 2y y prime minus 5 y prime, and that's going to be equal to 2x. So I've done, I think that's the second step. Yeah, second step. Now I'm going to factor and then solve for y prime. So I factor, you notice everything here has one y prime in it, so I can factor it out. So this left side is really y prime times 3y squared plus, I take a y prime out of that, I'm left with 2y minus 5, and that's equal to 2x. And then I can just divide both sides by this term here. I'll write it out here. I won't normally write all these steps out. 3y squared plus 2y minus 5 on both sides. These cancel out, and I'm left with y prime equals 2x over 3y squared plus 2y minus 5. And this is dy dx or y prime. It doesn't matter which one we say. Since this problem said find dy dx, it's just nice to write that down. And this is dy dx. And if we think back for a minute about what we said in this first problem, we had like a point, but we didn't have a slope. So now we have this point 4, 3, and if this was not the example, but if it was, Now we have a dy dx, and it has x's and y's in it, of course. But that's fine because we had a point that was an x and a y coordinate. So we can use this now to find the slope of this curve at any given point x, y. So that's how this works. I'm going to break this video here, come back and do some examples.